We're we're going to go ahead and get started. And once again, welcome. We are excited to have you here today. My name is Jessica Swan, and I am your community manager for the Infiniscope project. Today, we gather together for the third presentation in our series for the Heliophysics Big Year. So if you're not aware, the Heliophysics Big Year actually started last year. And actually, it started in 2023. That is last year, with the annular eclipse that happened in October, continued through the total solar eclipse in April, and will conclude when Parker Solar Probe makes its closest approach to the sun on December 24th of this year. Also, over the course of this year, and I think even into next year, we are approaching solar maximum, which is why we see so many great aurora. Our guest speaker with us here today is Vincent Ledvina. I'm going to tell you a little bit more about him here in just a second, but Vincent's going to talk with us today all about the aurora, which is nature's most spectacular light show. Before we do that, just a brief overview of what is Infiniscope and what does Infiniscope offer. So we have a whole slew of classroom-ready content. So if you're looking for digital learning experiences or you just want to explore on your own, we have many different learning experiences available so you can investigate Earth's interior. You can check out things like why do seasons occur? How do these eclipses work? We also offer things in Spanish. So if you prefer Spanish, we have that available. And one of our most recent learning experiences is on ocean acidification. Not only do we create content, but we also provide tools for educators to create their own digital learning experiences. So our two tools are Tourit and the Simple Lesson Builder. The Tourit tool allows you to create your own virtual field trips. And then the Simplified Lesson Builder allows you to actually create interactive digital lessons that leverages intelligent tutoring to kind of create your own, choose your own adventure style sort of lessons. We do offer training on all of these aspects, so do be sure to check out the Infiniscope events page to learn more about upcoming opportunities. And without further ado, I would like to introduce you to Vincent Ledvina. Vincent is a space physics PhD candidate and hails from University of Alaska Fairbanks. And with that, I'm going to go ahead and turn it over to you, Vincent.
All right.
Love
Thank
to
you
hear
so
from you.
much. Yeah, thanks so much for the introduction. I will begin sharing my screen and we can get started. Yeah, my name is Vincent Ledvina. I'm a PhD student here at the University of Alaska Fairbanks, which is where I'm calling from today. So good morning or good afternoon. It's currently 9 a.m. here in Alaska, so probably a few hours behind most of you, but I'm really excited here today to talk about the aurora, something I'm super passionate about. So just a quick outline of what I'll be talking about today. I'll be going over a little bit more about my background and sort of how I became quote unquote the Aurora guy, because that's what some people call me, and just share some really cool adventures and obviously some really cool photos too of the Aurora and all the Aurora chasing I've done. And then I'll go into really the science, which is what is space weather and what is the Aurora. It's really interesting because the Aurora is not only beautiful, but there's really interesting science behind it, and also space weather can affect your daily life. Then there's going to be a fun activity, and then we're going to get into some weird kinds of aurora and also how you can be an aurora scientist, and you will all be aurora scientists today. So my aurora origin story started all the way back in 2003 when I was 4 years old. So I was growing up in Minnesota, and I actually saw the aurora when I was trick-or-treating during this Halloween storm. There was a really big solar storm, October 31st of 2003, and I remember seeing the aurora sort of dancing above my childhood home in Minnesota and not knowing what it was. So I later learned it was Northern Lights, and I just became really interested in the outdoors, camping, nature, the stars, astronomy. I was in Boy Scouts. I was always out, always outdoors with my camera, taking photos of the natural world around me. And I became really interested in photography when I was in middle school, developed a passion for that. And then I really discovered auroras and space weather sort of around the same time. And everything sort of coalesced into this passion of aurora chasing. I took my first aurora photo when I was 16, and then I moved to North Dakota to go to school there for my bachelor's and study physics. And then while I was at UND, University of North Dakota, I sort of became this aurora guy figure. I started taking photos of the aurora, going out in the middle of nowhere, trying to chase these northern lights. And then at one point, the University of North Dakota posted one of my photos on their site, on their website, and on their Instagram. And then all of a sudden, I had people on campus coming up to me asking me if I was quote unquote that aurora guy. And my friends made fun of me. They said, "Oh, you're this aurora guy now." And at first, I was kind of hesitant, but after a while, I realized, I just do aurora stuff. This is like my passion, and I've just been interested in it for so long. So I've now embraced the moniker, the aurora guy. So I did a lot of aurora chasing when I was up in North Dakota. Had a lot of really great internship opportunities as well. Interned with the National Solar Observatory. I was a NASA summer intern. Interned at a company in San Diego, and got a lot of experience with space weather while I was an undergrad. And aurora chasing has taken me a lot of really cool places. I've seen the aurora in some really crazy locations and done some crazy things. So one of the coolest things I've done was go to Churchill, Manitoba, right on the Hudson Bay. So the image on the left there is actually looking over the Hudson Bay. And that's in northern Canada where polar bears are. So while we were here this time in March, we didn't see any polar bears. But we did see polar bears in September when we were there. This is in 2022, later in this year. So I saw 4 polar bears. One of them was about as close as you are probably to your teacher right now. We almost ran into them as we were rounding a corner. So yeah, these things are massive. They're beautiful, but definitely kind of extreme aurora chasing up in northern Canada. But the photos were amazing. And if you've never seen the aurora, it's this vibrant thing. It's not just static either. It moves. It sort of swirls around the sky. It can have really cool rapid motion. It's just beautiful. So that image on the left, or sorry, that video on the left is a video, a real-time video of the image on the right. So, with one camera just taking a still photo, you don't get the full experience. You really have to be there and look up and see this thing move, because it is just amazing. So these photos and videos that you're seeing now come from northern Alaska. I was up in Fort Yukon staying at an Air Force base up there for a few weeks, helping out with the NASA sounding rocket campaign. So that was really, really cool, which was also in 2022. That's above the Arctic Circle. And now I'm up at the University of Alaska Fairbanks, studying space physics, going for my Ph.D. I actually live in a town called North Pole, which is really funny to say, because it's, we get a lot of, actually the post office in North Pole gets all the letters from Santa. So it's pretty funny, over 50,000 letters every single year. And I'm sharing my love for the aurora. I just love this stuff. I think it's so cool. It's just beautiful, but it also is so scientifically interesting, and it also can affect your daily lives. So it's not just a pretty sight in the sky. It really touches the lives of so many people in so many different ways. I'm a photographer. I do photography professionally. I'm a citizen scientist, so I'm using my photos for research and collaborating with scientists. And you can all do that as well, which I'll be talking about later. And I'm also researching the auroras as well. So space weather refers to conditions around a star like our sun and its interplanetary space that may affect space and ground-based assets as well as human life. But really, that might sound like a mouthful. Really, it just boils down to the aurora. The aurora is such a good way to express space weather. It really ties everything together. It not only shows what's going on in our atmosphere, but it shows the energy coming from the sun going down into the Earth's sort of magnetic shield, all the electricity from space. It really ties everything together. So when I say, if you don't know what space weather is, just look up and look at the aurora. And it's a lot more than the aurora, of course. There's all sorts of things going on in outer space, which I'll talk about briefly. But just to give you, just to sort of whet your appetite, there's incredible space missions like Parker Solar Probe, which will be making its closest approach to the sun later this year, actually on Christmas Eve. There's solar flares, big explosions of plasma called coronal mass ejections. There's shock waves. There's giant magnets in space. There's all this stuff going on. So space is not empty. Space is full of these things called space weather. And it all starts with the sun. Just like we have just like we have weather on the Earth, we have rain and clouds and storms. The sun also creates similar weather in space, rain clouds and storms and wind. And really, the sun is what drives all this. The sun is what drives all this space weather. And from the ground, we obviously know what the sun is, and we see it, and it just looks like this sort of white disk, this sort of bright thing that you're not supposed to look at. But when we go out into space, scientists have these special sunglasses they can put on their instruments and their telescopes, and they can see the sun in a totally different way. So what we're used to is sort of, a white disk or this continuum, this sort of yellow sun here. But when you put on different filters, you can see the magnetic fields on the sun. You can see all the energy coming off into outer space in really cool and unique ways. And the sun is not just this static object, it's really dynamic. So when you put on these special sunglasses, you can see all this activity going on the sun, these explosions called coronal mass ejections, solar flares. You can see that the sun is sort of bubbling with all this energy. You can see that the surface is not just a perfect sort of circle. There's all these little flares and little tendrils coming off. So the sun is not just the static thing. It really is ever changing on the order of minutes, hours, even seconds. And the sun really blows a wind through space, which is kind of what space weather is all focused around, is this idea of solar wind. The sun gives us warmth and life, but it also gives us space weather. The sun is constantly changing, as I was saying, and it creates this wind that blows out called the solar wind. It's almost like if you have a hot cup of coffee, and that coffee in the center of the mug is the sun, and that steam coming off is the solar wind. So it's usually calm, and it sort of just flows around all the planets in the solar system, out to the very edge of the solar system. But sometimes it can be really strong and fierce. And the solar wind carries with it charged particles, which have magnetic fields and electricity with them. And Earth has its own magnetic field. So you can imagine when these two magnets essentially come together, you can get interesting things going on. And Earth is thankfully protected from this solar wind, which can carry with it a lot of highly charged particles and radiation. Luckily, we have a magnetic shield. It's kind of like a force field that protects us. Earth has its own magnetic field. You've all used a compass before. Well, that magnetic field extends out into space and sort of forms a bubble around us, which is called the magnetosphere. So when some of the sun's wind hits our bubble, some of the electricity in the wind sort of flows in. And when our magnetic shield charges up from this wind hitting it, sort of compresses it, we can get auroras around the geomagnetic poles. And so what is the aurora exactly? Well, it's nature's most beautiful light show, but it's really formed the same way actually that a neon lamp works. You have charged particles from space. These charged particles are streaming along magnetic field lines like surfers on waves. So you have all this energy from the solar wind. It hits our magnetic shield, and some of that makes it through, and it gets funneled over the poles. This energy comes down into our atmosphere, but luckily our atmosphere is also protecting us. So it eventually hits particles in the upper atmosphere and sort of energizes them, and in that process releases light in specific colors. So we have nitrogen atoms that glow red and blue, and we have oxygen that glows red and green. And you can see here on the right, the different colors actually occur at different altitudes. So red is usually above the green, which is above this, what's called a nitrogen fringe, which is below 60 miles. So if you've ever seen the aurora really, really dance, you'll actually see it sort of grow this little fringe at the bottom, which is caused by really high energy particles coming down and piercing our atmosphere. And the auroras are created really high up in the atmosphere. So I was saying, particles from outer space. Well, our atmosphere starts way, way high up above our heads, actually. So we breathe air down here in the troposphere, which is, barely registering on this graph. But the aurora really occur all the way up here in the E and the F regions. So this is 15 to 50 times higher than the plane flies, which means that if you want to see the aurora, it has to be clear outside. You can't see it when there's clouds because the aurora occurs above the clouds. And the ionosphere is called the ionosphere because there's ions or charged particles that make up this layer of the atmosphere. So this is also electrified. So when you have two, sort of, I guess, like electric currents coming together, one from outer space and one in the atmosphere, it can cause the gas to glow in specific colors like green, red, and blue. And it's exactly the same way that a neon lamp works. It's just that in this case, our electricity is coming from outer space, from Earth's magnetic field. And in the neon lamp's case, it's coming from the wall, right? And again, the neon lamp can glow specific colors as well. So it's just like a giant neon lamp in the sky, essentially. And you can see the aurora every single night if you wanted to. You just have to travel to a place underneath one of the auroral ovals. So when this energy comes in, it's funneled towards Earth's poles. So that's why you see aurora in places like Alaska or Norway or Iceland all the time, because it's underneath these auroral ovals. Of course, it needs to be clear and dark. To see the aurora, you can't see it during the daytime, and it needs to be clear. You can't have any clouds. And during what are called geomagnetic storms, when the solar wind blows really hard and when there's sort of these gusts of solar wind, which I'll talk about later, you could actually see the aurora from your own backyard. These auroral ovals expand, and the auroras can be seen from lower latitudes. So the sun can get really angry. These gentle breezes of space weather can turn into giant storms. The sun sort of releases these sneezes, which are kind of big clouds of charged particles out into space. And these usually take around 1 to 3 days to reach Earth. And when they come close to our planet, this sort of sun sneeze has its own magnetic field and its own sort of magnetic bubble, and it can sort of bounce off our magnetic field, or it can sort of link up, and all that energy can then flow down over the poles into the poles and charge up the aurora really, really strong and cause those auroral ovals to grow and expand. So we saw this happen actually just last week. We had auroras as far south as Arizona and as far south as Cuba and Puerto Rico. So that's not normal, right? We had one of these really, really strong sun sneezes. And so, yeah, I was just saying last week, I should have updated the slide because it seems like we've had tons of auroras this year. We've had two really, really big storms. We had one in May, and then we had one exactly 5 months later, just last week on October 10th. So we've had some really nice space weather that have given us some really great auroral displays. And that's because we're in solar maximum. So Jessica earlier was saying, we're in this heliophysics big year. Well, actually, NASA and NOAA just a few days ago declared that we are in solar maximum officially. So that means that the sun is more active. It goes through this activity cycle. You can see here, there's sort of high periods and there's low periods. And right now we're in one of these high periods. So that means that there's more space weather activity and more chances of these big, strong auroral displays. And space weather can affect you. It's not just auroras, but space weather can cause issues for technology in outer space and on the ground. So it's important that we study what the aurora is doing and also what space weather is doing so we can better understand these impacts. And one really famous event was the Carrington event in 1859, where we had a sun sneeze or a coronal mass ejection that was so strong that all the technology on Earth, essentially, which was just telegraphs, were knocked out. And auroras were seen basically around the entire world. So you can see here there was a newspaper clipping that just highlighted that. Auroras were so bright you could read the newspaper underneath them in Boston, which is not normal. So now this is kind of going on to our activity. What I would like you to do, and I think we can post the link in the chat, is we have some aurora photos that I've compiled in a slideshow. And you can just go to this link, bit.ly/aurora-activity, which will pull up a slideshow of these aurora photos. And what I want you to do is just, whether that's individually or in small groups, go through the photos and just kind of look at what you're seeing. Colors, brightness, shapes, they're just going to be photos of the aurora that I've taken. And you can just, comment to yourself or however you want to do it, sort of what you're seeing. And this will all make sense in about 5 minutes when we reconvene. But yeah, just spend 40 to 60 seconds per photo. I think there's 8 photos in there. And just sort of, make some observations, right? What kind of colors are you seeing? Are the auroras in one line? Are they multiple lines? Is it a really bright aurora? Is it really dim? What season is it? Is there snow on the ground? Things like that. So we can all look at those photos and then in I guess 4 minutes or so, come back and I will tell you what I was thinking for all the photos. So I've also done this activity, so I have my own thoughts as well. So it'll be interesting.
Okay, everyone, I've dropped the link over in the chat, so you should be able to click on that and access the images. And we'll be back in 4 or 5 minutes.
hopefully you all got a chance to look at the images there in the slide deck. So these are all images that I've taken around, well, actually, not just around Fairbanks, Alaska, where I live, but this one was. So this was taken just last winter. And if you notice, it's really very green. It's really bright. It's almost so bright that the snow is green. So that's something that we experience up here in Alaska is when the aurora is really bright, you can actually see the snow glowing, which is just really, really cool. And also, if you notice, there's really no aurora to the left of this big aurora here. It's obviously winter because there's snow on the ground. There's some sort of fuzzy aurora kind of to the right of these main bands here. You can see that within these bands, there's a lot of like substructure, right? A lot of really fine details. Like, and we're going to see that throughout all these photos is that it's not just, just one line. If you actually look very closely, there's sort of bands, there's little lines, grooves, little kind of ripples and things like that. For this one, much different, right? The aurora is not as bright. You can see the snow was very green in the last image, but it's not in this one. So that means that the aurora is probably much dimmer. There's more stars as well. It means that maybe we were using a longer exposure because the aurora wasn't as bright. A longer exposure with our camera means that we can let in more light and also means more stars. And there's also some glow over here. So maybe that's light pollution. It's not green. So maybe it's probably not aurora, right? There's some red colors as well, which we didn't see in the last photo. And obviously it's winter. Now this one is way different. This one's mostly purple aurora, which is really, really different. We can even see a little bit of blue here. We also notice that the aurora seems to be sort of streaming down from like one point. It almost looks like rays coming down, like almost like sunbeams or something like that. So that's different. We can also see that we're in like a campground or something. Maybe that doesn't have to do so much with the aurora, but might tell us about where we are, help pinpoint the location. Looks like we're in the winter time again. There's no snow on the trees, so maybe it's later in the winter since the snow is blown off. That's kind of Fairbanks insider knowledge, or I'm not expecting you to have realized that, but there's also some fuzzy or diffuse aurora kind of, towards this tree line here. We don't really know which direction we're facing, so maybe this is north, maybe this is south. It's kind of hard to tell just from this image. Now this one is very different, right? There's no green at all in this one, basically. Maybe a little bit at the bottom. So you might be able to say, okay, well, remember that color diagram that I showed you where you have the green and then the red. This kind of shows that, but most of it's red. So maybe the particles coming in aren't able to make it to those lower altitudes. So maybe they're really low energy particles, right? They aren't able to pierce as far down into the atmosphere. So yeah, and this aurora looks to be pretty bright. The ground is actually glowing red in this case, not green. There's a lot of stars. You can even see this little galaxy right here. This is Andromeda. Now this one is really weird too. We got a green aurora, so we're right on track there, but a lot of weird sort of curly structures like a snake. It's very twisted. There's some aurora glow maybe to the right of the image here, and of course the ground is green again. This one was actually taken in my backyard just a few weeks ago, and it almost looks like the bat symbol. And you can see the image is sort of warped. It almost looks like we have like a fisheye lens going on. It's not winter. The snow is, or there's no snow. The ground isn't frozen. It's now snowy here. We just got snow yesterday. So if I were to take an image in my backyard now, there's tons of snow on the ground now. So fall does not last too long up here in Alaska. But there's also some weird like substructures, like almost looks like a sort of lace dress or something. There's like all these weird sort of ripples. This one is really cool. This was actually a few days before the last image. I took this one. Cool pink colors here. This shows that color diagram perfectly. You have the green, then you have the red, and then you can actually get a mixing between the blue and the red to get this purple. So yeah, really interesting colors here. A lot of stars. It seems like the whole sky is full of aurora. And I think somebody compared this to a hurricane. Yeah, this is what I like to call the aurora cinnamon roll. So yeah, the first thing that jumps out at you is that this is a really interesting shape. It's like a whole curl, a whole spiral, a whole cinnamon roll. I must have been hungry when I was thinking about that. But yeah, I saw this actually in Churchill, Manitoba. So this was, we actually saw a polar bear later this night. So that was pretty interesting, a little scary, but this aurora was awesome. It was super, super bright. It's actually so bright that it's white on my camera, which means that it's a little bit overexposed. So there's aurora kind of filling the entire sky here. There's some here on the left, maybe a little bit here on the right, but really it's this spiral that's just, so striking. And, looking at these aurora images, you might say, okay, what's the point of doing this, right? Well, this is actually how scientists do research. I mean, I do this every single day in a grad school, and looking at, what kind of auroras we're seeing. And, the shapes of the auroras matter a lot. The colors matter a lot. And what direction the aurora is in, how bright the aurora is in, the height of the aurora. If you're seeing a lot of red auroras, those occur really high up in the atmosphere. So that means the aurora is really, really tall, and it's occurring in a different location than the green. So that's really important. The patterns in the aurora kind of correspond. If you think about the aurora as sort of this raining down of electricity or particles, the patterns in the aurora, those spirals, kind of correspond to the clouds in outer space that are raining down those particles. So that's kind of, going back to the idea of space weather, is that we not only have the rain of the aurora coming down, but we also have the clouds that can produce the rain. And the types of auroras we see in the atmosphere correspond to the types of clouds in outer space that are responsible for that particle precipitation of the aurora. So yeah, what you guys just did is aurora science. That is really what it boils down to. And that's half of the battle, is just figuring out what is going on. And we use imagery really primarily to do our research. We take photos of the night sky, and then we take those photos back to the lab and say, okay, what did we just see? And we go and apply special filters to those photos. We take videos, and we can see the evolution of the aurora. So this is actually, this circle here is if you imagine you're laying down on the ground and you can see the whole sky as sort of a fisheye all sky lens, kind of like a planetarium, you can see the aurora throughout the entire sky. So this is really common to see these all sky images. And when I was in Fort Yukon, Alaska, I was doing this research in this type of analysis that you all did, constantly taking photos of the aurora and figuring out, when we see a specific type of aurora, we have to launch that rocket, because that's what we want to see. So what you all did is basically what I've been doing for the past 4 years, what I'll be doing for the rest of my PhD. So it's really not that hard. It's really fun. Just going through and looking at aurora photos is real science. And through this, aurora chasers are out there looking at the aurora all the time and have discovered some really weird things. So that's what I'm going to be talking about next, are some weird types of auroras. We all saw pictures of sort of normal auroras. They all look different, but these are just weird ones. So we have Steve, and I kid you not, this is the real name of the thing, Steve. We have fragmented aurora-like emissions, which are these little green, like tic-tac type looking things. We have what's called Ragda, or red aurora with green diffuse arc, which is this formation. And we have these dunes. So if you've ever seen the aurora, you can take a photo of it and submit it to online databases and projects, and have your photos used for research. And you can help discover things like these weird types of aurora. So let's get into what Steve is. I'm sure there's some chuckles going on. This is a real thing. It stands for Strong Thermal Emission Velocity Enhancement. It's not necessarily a new type of aurora. All these auroras have occurred for as long as the Earth has had a magnetic field, right? And the sun has been blowing out a solar wind. But really, we didn't notice Steve until recently in 2018. This is a very new discovery. We had aurora chasers in Alberta that were noticing this weird whitish aurora that was appearing to the east and to the west instead of to the north, like the normal aurora would. They started taking photos of it. They said, this looks a lot like a proton arc, which is something that's discussed in the scientific papers. Then scientists actually, they sort of came to these aurora chasers, and they were like, hey, what is this thing that you're seeing? And the aurora chaser said, oh, it's a proton arc. And the scientist said, no, that's not a proton arc. This is something completely different. We're going to sort of go back to the lab and sort of investigate this. And then in the meantime, the citizen scientists, these aurora chasers, said, well, what are we going to call this thing? And then they said, let's name it Steve. So if you've ever seen the movie Over the Hedge, Steve is what's beyond the hedge. It's sort of the scary, it's like all the humans, right? The new development moving in. And to make it sound less scary, they name it Steve. So that's where the name comes from, is this childhood movie called Over the Hedge. So that might be beyond all of your times, but I remember watching that when I was a kid. So it's actually not a normal aurora. I was saying that auroras are formed by electricity coming down from outer space into the atmosphere, sort of like raining down. But Steve is actually produced by a white hot flow of gas. So if you've ever heated up metal really, really hot, it starts glowing. It's the same thing. In the Earth's upper atmosphere, we have these rivers of gas that are so hot that they start to glow white, and that's why Steve looks white instead of a normal green color. So yeah, auroras usually occur and emit colors in very specific wavelengths. So green, blue, and red. Basically that's it. But Steve is sort of a combination of all these colors, and it's a white emission. We have friends of Steve, so the family of Steve and the friend network of Steve is growing. We have Ragda, which is a red aurora with green diffuse arc. We also have these things called stable auroral red arcs. So these are mostly subvisual, although you can see them if they're bright enough. And I know that SAR arcs were visible during the big storm last week. So if you saw a really, really red aurora, you might have actually seen a SAR arc. And these SAR arcs are known to evolve into Steve. So they're kind of like Steve's dad, or like the precursor to Steve. So aurora chasers are, looking at all these aurora photos, and they're out there all the time, and they're discovering things that scientists haven't seen or haven't realized are important. So it's really, really cool. We have auroral dunes, and I'm not going to pretend like I'm an expert in sort of lower atmosphere things, but you have these gravity waves that propagate up from lower altitudes. So you have these ripples, and sometimes you can see them in clouds, actually. If you've ever noticed like these really evenly spaced clouds, those are actually gravity waves. But if they're high enough up in the atmosphere, they can be seen in the aurora, which is really, really cool. And they look like sand dunes. So these were discovered in 2020. We also have fragmented aurora-like emissions, or FAEs, and these are my favorite. I will admit my bias here, but they're like little green tic tacs or blobs, and they're just really, really strange. What's really interesting is that, when the aurora particles come down, this electricity comes down from outer space. It's relatively aligned with Earth's magnetic field. So like I was saying, these surfers are riding waves, right? These waves are coming down at very specific angles, and we can sort of map these waves out into space. Well, these tic tacs are like not aligned at all to these waves. They're sort of coming off of the side like little spokes on a wheel. So it's really strange, and we don't really know what they're caused by, but we need more observations. So I'm part of this group, this sort of international group of scientists that's looking at aurora chasers photos and asking people to look back and see if they've seen these little aurora tic tacs, as I like to call them. But curiously enough, they look like the streaks seen in Steve's picket fence. So I mentioned this white emission, but Steve also has these picket fence features that come down right below that white streak. And sometimes they look like little messy exclamation points, where you have the streak, or sorry, you have the picket fence, and then this little dot or blob of aurora that sort of comes off at a weird angle. And that might be very similar to these fragments that we're seeing. And you can do aurora citizen science. You can be a part of all these investigations through projects like Aurorasaurus. So I actually was an Aurorasaurus intern back in the day. You can visit aurorasaurus.org, and you can report whether you've seen aurora or not. And those reports go on a map. So you can see here, this was actually during the May 2024 event. We had a huge geomagnetic storm, and over 5,000 people reported the aurora on Aurorasaurus. And that helps aurora chasers understand where the aurora is being seen. And also a map of these aurora reports over time can help scientists understand, like, if there's a big space weather storm, what is the aurora doing as a response, right? So if you go to aurorasaurus.org, even saying that you haven't seen the aurora is super important. So, if it's cloudy, but there might be aurora above your head, go to Aurorasaurus and say, I'm really sad I'm not seeing the aurora right now, but I want to help science. I've definitely been doing that recently. It's been super cloudy here in Fairbanks, but yeah, your reports are really helpful. So this is one way where you all can be directly involved in aurora science by visiting aurorasaurus.org. And you all could become aurora chasers as well. All it takes is a love for the night sky and some patience, and it's easier than you probably think. The science is super interesting, but the auroras are always there. The auroras, have been doing their thing for billions of years. So all it takes is travel to Alaska, travel to Iceland or Norway, and just sit out underneath the sky and wait for the auroras to appear. Because up here in North Pole, Alaska, where I live, literally every single night there's aurora. You just have to wait. Sometimes you don't have to wait long. They're right out after sunset, but other times it's just sort of a waiting game, and you have to have some patience. You can also wait for space weather to become really intense, and those auroral ovals to expand down to your latitude. So, I'm sure most of you heard about the aurora last week. You don't have to wait, hopefully, too much longer for one of those events to happen soon because we're in solar maximum, but you don't necessarily have to travel to Alaska either to see the aurora. You can maybe see it from your own backyard. And you are all aurora scientists now. You all just looked at photos of the aurora and were able to say like what colors were you seeing in the sky? Was it a green aurora, purple aurora, red aurora? And that's really what it boils down to is looking at aurora photos and just sort of observing what you see, going out into the natural world and making observations. And this is something that you all can do. It's something that I realized I wanted to do fairly early because I just had this, love for science, the night sky, and astronomy. But there's so many pathways you can choose to study this phenomenon of the aurora borealis and also space weather in general. Space weather is very important to study, and it affects all of our daily lives. I didn't really touch on this a whole lot before, but auroras, when the aurora is really, really strong, it sort of tells us that Earth's magnetic shield, our force field, is working really, really hard to protect us against space weather. So we can use the aurora as sort of a tool to understand how the Earth is responding to a big space weather storm. And if you're really interested in exploring more projects, there's a bunch of different ones out there. This is sort of a bunch of these different citizen science projects. So Aurorasaurus is one, but there's also the Globe at Night project, which helps map light pollution. There's the HARP project, where you can actually listen to these sort of space weather clouds in outer space. They've taken these data from satellites in outer space around Earth, and they've turned them into music, and you can actually listen to them. And when you hear specific little chirps or tones in the music, that actually corresponds to something scientifically interesting. So you can mark those and help scientists better understand what's going on. But there's a huge plethora of citizen science projects that you all could get involved in if this is something that you're interested in. And yeah, I'm happy to talk about that more after the presentation. But really what it boils down to and what I want to get across is that now is a really, really good time to be an aurora chaser. It's a really, 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 really good time to start looking into heliophysics and observing these natural phenomena that are gracing our skies, and not just the skies in the northern latitudes in the Arctic regions, but when we have these really extreme and powerful space weather storms, we can get auroras down to very low latitudes, like Arizona, California, Colorado, Utah, all saw the aurora last week, right? So we are in solar maximum officially now, and it's not just this year, but the next couple of years are going to be a really, really good times to observe the aurora. There's going to be a lot of activity. Space weather can affect your daily lives. It can, damage satellites in space. It can cause, power grid failures, just like other natural disasters here on the ground that we're more familiar with, like, hurricanes, for example. It's just space weather is not as well known, which is a shame because it's super, super interesting. And the aurora is a visual manifestation of the power of space weather. And you can all be space weather scientists. You've proven that today. And there's lots of contributions to be made through citizen science projects that you can get involved in, which I just showed earlier, all these different projects that you can participate in and help, aurora science and heliophysics move forward. So with that, thank you for your attention. And then I will have a page on my website. I'll be getting that up later today with tons of resources. This slide deck will be available. Those images that you saw earlier will all be available, and a bunch of other resources if you want to learn more about, let's say solar flares or coronal mass ejections, these things that, I just briefly mentioned earlier, but really could take an entire lecture, an entire hour to explain. I'll have more information on those on this website as well. So with that, thank you all for your attention. And I guess we'll move into a Q&A period now. So hopefully I can expand upon some exciting things that you all have questions about.
Yeah, absolutely. That was fantastic. Thank you so much for sharing all of that with us. And I do have a handful of questions. I'm going
Oh,
to try
great.
to organize them in some way that kind of makes sense so that they're clustered a little bit.
Sure. Okay.
So I'm going to kind of start with maybe the simplest of the questions, which is, so we talked all about the solar maximum.
Yeah.
And you also end your presentation saying, this is such an exciting time over the next couple of years. So how often does solar maximum occur?
Great question. So solar maximum occurs roughly once every 11 years. But I should stress that it's not just 1 year, that solar maximum. I kind of like to frame it in a low season or like a winter or dormant season on the sun, and then like a high summer or like active season. So, solar maximum is just one point. It's sort of the very tippity top of the mountain. But, you can imagine you're still climbing that mountain. You're still a very high elevation, right? So, the sun is very active for roughly 3 years. Sort of around the solar maximum time. So right now, scientists think that we are at that solar maximum, that sort of tippity top of the solar cycle. We won't really know for sure until we start decreasing in activity. But right now, we're sort of in that high season. So we've had about a year and a half of really active space weather the past, year and a half. And we're expected to see, another 2 years or so of really active space weather as well. And actually, there's some really cool research that shows that as the sun sort of goes down from this solar maximum towards solar minimum on this descending phase, that we see the most extreme space weather. So we
Hmm.
might be in for some more really, really big shows.
Oh, that's very cool. And then, so how
Yeah.
long, I don't know that you said how long is an actual cycle then?
Yeah, so
Typically?
it's every 11 years. So every cycle lasts roughly 11 years. It's sort of an average. So it could be anywhere from 9 years to 13 years.
Okay. And then, and the next question, follow on for that one is what causes the cycling?
Hmm. Yeah, so this is an area of active research. I'm not an expert in what's called dynamo theory, but actually, it's the same way that Earth's magnetic field is created. The sun has sort of this dynamo in its center. So, imagine like I guess these two magnets in the sun's center sort of rubbing together. Creates this global magnetic field that extends out into outer space, just like Earth has a magnetic field, which sort of forms a protective bubble around Earth. The sun has its own magnetic field that actually protects the entire solar system from an interstellar wind. So we're talking about interstellar space weather at this point. But so the sun's magnetic field is really important to why it has solar cycles, but also the fact that the sun does not rotate at the same rate at every latitude. So what I mean by that is that the equator of the sun rotates at about 24 days, but the poles rotate at about 34, 33 days. So that means that, if you're able to spin up the sun, the parts of the center are going really, really fast, and the parts of the poles are barely moving at all. And when
Hmm.
you have these magnetic field lines, they become twisted. As you start spinning up the sun, these magnetic field lines are usually straight up and down, kind of like a bar magnet. But as you start spinning, imagine you're taking that bar magnet and you're kind of twisting it around. And it just so happens that the rotation rate of the sun combined with these twisting magnetic fields creates these sort of 11-year cycles where the magnetic field goes from really straight up and down, kind of like a bar magnet, to just jumbled all over the place, which is why we get these magnetic field lines popping out of the sun's surface. And when that happens, that's in the solar maximum phase. So the sun rotates on average once every 27 days. If it were to rotate faster, like let's say every 5 days, our solar cycles might only be 2 or 3 years. So we're actually able to see that on other stars, these stars that we can sort of image them, and we can figure out how fast they're rotating. We can actually see big giant sunspots on these other stars outside of our solar system, because the faster you spin up the star, the more active it will be. So the solar cycle itself, it's really more complicated than that, honestly, but it's really a product of the fact that the sun is like a bar magnet and it doesn't rotate at the same rate. So you're kind of twisting up these magnetic field lines, and then you're untwisting them, and that sort of leads to this oscillating activity, which we call the solar cycle every 11 years.
Great. So then the next question is going to be, so when you show a lot of these pictures, we see that the aurora are happening at different vertical positions
Yeah.
in the sky and or in the atmosphere. So what is the cause of their location, like either where we view them or actually where they are in the atmosphere?
Yeah, that's a great question. So, yeah, auroras occur at multiple heights. So, really from 60 miles to 300 miles in altitude. And the height of the aurora is determined by how much energy that, sort of particle, or how much energy that electricity from outer space has, so that it's able to go down further in the atmosphere. So, if you don't have a lot of energy, that particle is going to, collide with all this gas in the upper atmosphere and maybe only make it to 200 miles. But if it has a lot of energy, it's going to burrow its way down until it reaches an area of the atmosphere that's thick enough where it'll eventually stop. So particles that have a lot of energy might create all these colors along their way down. So they might create red and green and purple on the very sort of pink purple on the very bottom, that nitrogen fringe. And also, how they appear to us really depends on the perspective, right? So the aurora really occur in these auroral ovals that are sort of they kind of encircle the geomagnetic poles. Right over Fairbanks, for example, we're right underneath one of the auroral ovals, but places like Iceland and northern Norway, and then we also have an auroral oval in the southern hemisphere, which is basically entirely over Antarctica. If you're right underneath the aurora, you sort of just see what's called an aurora corona. This aurora just spreading out in all directions. It seems like it's sort of literally raining down on you from a single point. But if you're far away from the auroral oval, you'll start seeing those striations, those sort of green, red, sometimes blue or purple layers. And then if you're really, really, really far away from the auroral oval, you might only see the red because the curvature of the Earth starts playing a role. As you go further and further away from the auroral oval, you start only seeing the very tops of the aurora, which are red. So it's very typical during these really, really big geomagnetic storms that although the auroral ovals expand to maybe, let's say, instead of being over Alaska, they're over somewhere like Seattle, right? If you're in Arizona, you might actually be able to see that aurora, just the very tops of it. So it might just appear red. But yeah, the colors are due to the altitudes and also the gases that are being excited. So we breathe oxygen and nitrogen down at the ground. Well, those are found all throughout the atmosphere. And those oxygen and nitrogen atoms glow different colors. And those colors are usually just green, red, and blue, but they can mix together and form essentially an entire rainbow of colors, which we can see in the aurora.
That's great. So I'm glad you mentioned Arizona because that's where we're
Yeah.
located. And so I can connect personal experience with a number of the questions that I also see, which is
Uh-huh.
about photography. So here
Yep.
in Arizona, as you said, we received red. And I think
Yep.
the past time we actually got a little green, but I wasn't here in the state when it happened. And the other thing that we notice is it was difficult to see with the naked eye, but our camera set
Yeah.
could catch it. So there are a lot of questions about like, what is your camera setup? You know, for those who live outside of this space, where you're at, do you actually see it with the naked eye? Is it enhanced by camera? So just kind of tell us about the photography aspect.
Yeah, that's a great question. And one that I get so often is, can you actually see it? Because even though you can have these really big space weather storms, the aurora sometimes is all over the place, but very faint. And what happens is usually that's the case. Usually the aurora is pretty faint. I can pick it out with my eye, but the camera definitely sees more. And then during what are called auroral substorms, it's kind of like a storm within a storm. You have this big burst of activity, and the aurora just goes nuts. It starts. I wonder if I can pull it up. This was an auroral substorm. A lot of these photos actually are auroral substorms because that's when the aurora looks the best, essentially. But this video here on the left was actually taken during one of these substorms where the aurora just goes completely crazy, and you can definitely see the greens. You can see all the colors. You can literally see the ground turning green as well. So cameras will pick up more colors when the aurora is really faint because our eyes are just not designed to see in the dark. Cameras do not have the limitations that our eyes have with seeing really, really faint colors. Our eyes kind of turn off the color vision when it's really, really dark outside. So we only see black and white, and we just don't see as well in the dark anyways. So we might not even see the aurora. It might just look like a cloud or might not look like anything, but cameras don't have those limitations. You can basically tell your camera to tell your eyes to take a photo for 30 seconds. If you could do that, you could see exactly what a camera could see, but we can't do that, right? We can't control the shutter speed of our eyes. So cameras can do that, and really long exposures can reveal very, very faint auroras. And yeah, when it's strong enough, you can see all the colors. We had some really, really gorgeous red aurora last week, which I could definitely see with my naked eye. And that was crazy. I had never seen such vibrant reds before. And it was honestly a little bit creepy too. As you look around you and the entire sky looks like this crimson red, it was just very strange. So when the aurora is strong enough, honestly, your own eyes do a better job than the camera in some aspects, because you cannot see the motion of the aurora with just one photo. So that's something that your eyes have an advantage over.
Great. And I think we have just two last questions here,
Okay,
and we've got about 6 minutes, so that's probably just about right.
sure.
The next question I have for you is about climate change. So does
Yeah,
climate change actually have any effect on, the amount or the color or any aspects of the aurora?
that's a great question. I know there are a lot of researchers looking into that. I'm not super certain whether or not climate change affects the aurora in a major way. I'm pretty sure, because the aurora is occurring so high up above our heads, it's not affected by a lot of climate change induced weather, right? We're seeing, more extreme, like, thunderstorms, tornadoes, and hurricanes and things like that. But the aurora is really above all that stuff and is really controlled by the sun, and sort of a function of how active the sun is. So I don't think that climate change will affect the aurora in any major way. It certainly will affect aurora viewing. If your area is getting more cloudy, well, you cannot see the aurora if there's clouds, over your head. So you might sort of miss out on some displays because of climate change and just having clouds in between you and the aurora. But I think, there are some subtle nuances to that. As we're seeing, changes in the lower atmosphere, those can propagate up to the upper atmosphere too. So these upper layers of the atmosphere where the aurora are occurring might be slightly warmer or cooler, over time as the climate changes. So it's possible that there are some minor effects, but actually, thankfully, I don't think climate change will affect too much, with the aurora.
Okay, continuing with our theme on cutting edge science here. A question about the Tic Tacs. So the
Yes,
question here is it possible that the Tic Tacs are caused by events outside of our solar system?
that's a good question. That would be pretty cool. I do not think that they would be caused by anything outside of our solar system, just because the sun thankfully protects us with its magnetic field. It sort of forms a protective shield, just like Earth does. We have a magnetic bubble around Earth, sort of protecting us from the sun. The sun protects the entire solar system against what's coming in from the outside. So that sort of boundary in that bubble is way outside of even like Neptune or Pluto. So I don't think there's anything really coming in, from deep into outer space, affecting the aurora on Earth. But it is interesting. We can see auroras on other planets, outside of our solar system potentially. So that is cool. So maybe we'll find aurora tic tacs on other planets. Who knows? But I don't think personally, that we're seeing any influence from outside of the solar system because everything is basically controlled by the sun.
Outstanding. Well, Vincent, we sincerely appreciate all of your time that you've spent with us today. This was so illuminating, understanding, learning more about the aurora. And I'm sure I speak for everyone out there. There's some great comments for you in chat. You should probably check those out.
Yeah, I will.
Lots of kudos for you. For those of you back in the audience here, I did drop a survey over in the link. Please do take a few minutes to complete our survey so that we can share your feedback not only with Vincent, but also to inform our processes. And finally, there's another link. So we have one more talk in the series for the heliophysics big year. I believe this one is happening, yes, next week. So Wednesday, October 28th at 10 a.m. Pacific time, 1 p.m. Eastern time. We'll be talking with Maya Levinson. She is predicting space weather and using computational models. She's going to share how she uses computer software to study solar activity and its effects on Earth's magnetic field. The solar interactions can create currents in the ground that might disrupt power grids, pipelines, and other important systems. By using these computer models to understand these effects, Maya's work helps us better predict potential disruptions, ensuring the safety and stability of essential services that we rely on every day. So be sure to register for that, and we will be concluding our heliophysics big year presentations with Maya. Thanks again, everyone. Thank you, Vincent. We will also send a follow-up email with a link to Vincent's site that will have all of the
Yep.
resources that included. You said it was going to be the presentation.
Yep. I'll have everything there. Yep. I'll have it by the end of the day. So if they
Great.
check in a few hours, it'll all be there. So, yep.
Outstanding. Well, thanks again. Bye, everyone. We'll see you next week.